The part of gate score booster series sessions. So I have conducted 2 sessions on computer organization architecture. So before this after this completion of this session, like you can also go through on COA, in which various important questions on important topics I have discussed. Similarly, I would like to discuss the most important areas from the operating system. We'll revise those topics by problem solving now. The main objective of these sessions to increase your score in the GATE exam, meaning to bringing the clarity on the topics by solving some important questions, some critical questions you can understand now. I would like to take the 3 sessions on operating system. This is the first session. The 2 more sessions I would like to conduct the upcoming weeks. Okay. So in this operating system part 1, so what I'm going to discuss here now, I'll be covering some topics from the chapters through what problem solving only now. From introduction to operating system, in which you might know the definitions, various classifications of operating system, correct, understanding what is the uniprogramming, multi-programming, right. The complete background of the operating system you might have known in the beginning of the chapter. But I'll be discussing some questions because GATE is focused more on the system call based questions, like especially on fork system call. The followed by process management, in which process concept related things and scheduling and IP synchronization and concurrency part, deadlock. These are the main topics comes under process management. So thank you, Mathan. Thanks for the updation. Yes, audio video is clear. Thank you so much. From the process management, these are the main important topics. Similarly, memory management of file system. So I'll be taking another session. So from this session, I'll be discussing some questions related to this one, related to this process concepts and CP scheduling algorithms. Till this only now. I'll try to cover up these 2 topics in another session now. IPC synchronization deadlock, I'll plan another session now. Okay. So I hope you have a understanding on this fork system call. But let's try work out this concept also by through questions. Okay. The first question I would like to take on the fork system call. So parallelly, you also try to solve this question. A process executing the following code. So into mean if fork and operator fork, the print IMS. The number of times IMS will be printed after executing above program is dash. Yeah. Parallel, you can also try it. How many times this IMS is printed? How many times IMS is printed now? Let us solve this question now. So look at how to attempt this one now. Look at how to attempt this question. So what do you do? This program, this entire program is there. Okay, sorry. This entire program, you treat this one main program. Okay, parent program you can say now. Okay, this is a P, parent program, you can say this. Parent program is running. How many times the IMS get printed, right? P is running now. P is a parent now. So let me use a binary tree to evaluate this program code. P is the parent, right? So parent code, if I start, you understand now, if condition, there is a fork statement. So I hope you know the basics. Whenever the fork is a system call, when system call is encounter, this fork definition is available kernel part of the operating system. That means mode shifting essentially required now. I know the procedure how to change the mode from user mode to kernel mode, right? When the fork is encounter at the time of compiler is replaced by a privilege instruction. It's called supervisory call. During runtime, SVC is the instruction get executed. This causing the interrupt. That interrupt is called software interrupt. When a software interrupt is occurred, we need to resolve this one. Relevant ISR, interrupt service routine, the exception will execute it. During execution of this exception, the mode shifting takes place. We have to shift from user mode to kernel mode. Locate this fork system call and execute the system call now. Once execution get over, now you have to return from kernel to user mode now. Now fork system call, purpose of the fork system call is to create another process now. So successful execution upon this fork system call, the new process get created, and the new process is nothing but exactly duplication of the original process. I hope this concept is clear now. The execution of the fork system call, what happens? It exactly duplicates the original process, including file descriptors, the status of the CPU, register information, whatever the parent was doing, everything is copied. Everything is copied. Right. Chalo, I'll work on fork. Fork means you would create process. So the created process, let's take the naming as C1. I'm naming as C1 now. Let me write the C1 code. C1 is what? Entire duplication of this one, right? The entire code is there. Let me shortcut form write if F1 logical end operator fork 2 or fork 3 is there, printf function is there. This is a simple code I'm taking now. So as also know, is a fork is a system call, it's like a function call. Any user defined function call can return something, right? Similarly, the fork also return from this what kernel mode to user mode. What is written? There are two things will be written. Actually, three. The two essential. What is two? Return value to the child process newly created value is 0. So now return value for a parent is a process ID. The child process ID you can say understand now. Okay. Now for this parent return value some positive integer. Positive integer nothing, process ID only now. So for this return value will be 0. So remaining parent is here only. Parent process not completed execution now. You can see, right? The parent is still here only, right? Parent process is not completed now. So now this is a binary tree form. You can see, you can evaluate level by level, left to right. Let me try again P1. One more thing understand, in the memory two process got created. We can start execution of the parent or child. This depends on the CPU scheduling algorithm. Execution can be done any order, but the termination of the among this process, parent should be at last. That's only one thing you understand now. I can start parent now. If a parent continue, what happens now? We must know importance of this logical AND operator. What is the logical AND operator says? Suppose A logical AND operator, B is the assumption now. If this A is positive, then you check for B. You check for B whether B is positive or not. If A is 0, don't check for B. That's a AND operator says. If left side is true or positive number is there, you just check what is B. If left side already is 0, not required to check for B. That's the meaning of this logical AND operator. So when it comes to logical OR operator A or B, if A is positive, no need to check for the B. What is B? If A is 0, then you check for B. That's the case of what? Logical OR operator now. So now we are looking at a parent code, right? Parent code I'm looking. Parent code I'm running, right? So parent. So now right part I should evaluate because left side is positive. I have to check for this one. B is a fork system call. So another process get created. That is naming as C2 assumption now. Now remaining parent is here only. P I'm writing like this. Process child code if you see same, if this fork 1 logical AND operator fork 2, I'm writing just or fork 3 is there now. Child 2 got created from this fork only, return value child process 0. For this return value is what? Positive. Positive is there now. Right. So parent child is there now. Parent child is there. Let me work out this. I want to go binary tree evaluation level by level, left to right. So this level left to right I'm going to try for C1. See what is C now? We are at here, right? Logical AND operator says left side is 0. Don't check for this B. It is not checking. That means you have to logical R. What is R? This entire part is 0 only, right? Logical entire part 0. When logical R operator says if left side is 0, check for right side. Therefore, it is checking for this one now. Checking for this one, nothing but something. C1 is as it is. Now another child is created, that is naming as, let's take C3. Okay. The C3 created because of this one now. So C3 code, if we see it, if fork 1 logical AND operator fork 2 or fork 3, correct. So C3 child return value is 0. For this return value is positive number is there. Positive number is printed now. Correct. So very good evening, Nishikumar. We have started operating system. The first one system calls. So you can see the question. Quickly you can see the question now. Just I'm asking number of times IMS will be printed after executing above code. Just snap it. You can take this one. Parallel you can work. Chalo. Now come to the point now. In this level, let me go left to right. Parent. What is the scenario of the parent? Parent, this is won't execute it because left side part is already positive. This won't check now. If this one now, what is this one now? Condition. So this entire, if condition is true or not, if condition is left side is true, right side is not checking, entire condition true, nothing but IMS printed. So now I'm saying that IMS printed here now. I'm going to C2. Where is C2? Here is C2 now. What happened for C2 now? What happened for C2? So C2 code I won't run now, C2. So C2, see left side is 0, right? Logical operator says that you have to check for right one. Logical operator left side is 0, you check for what? Right side. So therefore I'm keeping C2 as it is. C2 as it is. Now one more process got created, C4 here now, C4. Let me write the C4 code. What is C4 code? If fork 1 logical AND operator fork 2 or fork 3 is code is there now, followed by printf. Everywhere printf will be there now. C4 came from C2. C4 return value 0 is return value some positive number will be there now. Am I right now? I'm going for C1. What is C1 status? So left side not evaluated, right side evaluated, entire positive nothing but printf. So now when I run this C1, IMS is printed now. I'm going for C3. What is C3? So this we did not check the return value 0. Overall condition is false. Therefore, this printf function will not run. So C3 it will not run anything now. So this level over now. So this level over, right? Now I'll go to next level. C2. What is C2 code? C2. So C2 is our return value positive. Entire this condition is true. Therefore, this printf function executes. So IMS will be printed here now. Look at for C4. What is C4? This return value 0. Entire condition is 0. So sorry, very C4. Yes, return value is 0. Entire condition is false. Therefore, printf function will not run. So this C4 will not run, print anything now. So now all process get executed, right? So number of times. So number of times IMS printed is equal to how many? 3 times. Answer for this question is 3. Yes, very good, very good. 3 times printf is there. You are right. So I hope this is clear. So what we have to, so if you know the definition of the fork is not sufficient, we should also know that how my programming logics are there now. So number of times this printf function something executed completely depends on my logical operator and or, right? Am I right? Chalo, we'll move on to another question. Okay, this done. Yeah, okay. So even last session also I told we at IMS IMS GATE Academy offering all India mock test series for GATE 2026 aspirants. Total 12 test series we have planned it, which are completely prepared by our internal mentors, right? Okay. So this also as a schedule wise, every month 2 tests are launched, almost 7-8 test series on live. The remaining 4 has to become. Okay, who are interested, you can enroll to this because this is a time to test yourself whether you're doing correct or not. So all in the mock tests are, the full length mock tests are much important because we should learn. I'm 3 hours I'm able to sit for the exam or not. The sitting capacity we should observe it. Now switching between the subjects, example, entire operating system test sketch if you given, you're able to solve it. But if I mix 3 TOC questions or COA questions or maybe computer networks, immediately we are not able to jump. So we always try to minimize the contest switch time between the questions, right? Contest switch time we have to minimize it. So this minimization contest switch time between the question solving only possible when you attend multiple tests, multiple full length tests. Therefore, this full length tests are much essential for every serious aspirants who are preparing for GATE 2026. It's the right time to start. The December right time till January, you should practice this all the test. So I hope this is clear. Chalo, move on to next question. As I told, so we are offering the online classes. So which contain these are the main features we offered. The teaching plus exercise book questions and theory books are there. So for last previous year papers, full detailed solution PYQs are there. So especially main point of this IMS are 12 mentorship sessions given to each student and more than 130 online tests available, which includes topic level, subject level, multi-subject level, full length mock test. It's done. Shall we move on to next question? It is because some theoretical questions also important. From the process concept, we can expect the MSQ questions. Let's understand now. Which of the following is are true? Which of the following is are true? If the time quantum is extremely small, round robin can result in large number of contest switches. Is it true? In round robin algorithms, if the time quantum is extremely small, round robin can result in large number of contest switches. Is it true or not? Yes, true. So smaller round, extremely small, very small, more contest switches required, definitely now. The average turnaround time of set-off process does not necessarily improve as the time quantum size increases. Average turnaround time of set-off processes is not required to improve when the time quantum increases. When time quantum increases, average turnaround time of the set-off process does not necessarily improves as the time quantum size increases. Think on, tell me what is statement B is talking. Yes. Think, all of you. Is it true? Nishukumar, option B is true. The average turnaround time of set-off process does not necessarily improve the time quantum size increases. When time quantum increases, generally turnaround time also will increase, isn't it? Increases or decreases? Think. When time quantum increased. Okay, if you doubt, then think on C, option C. Average turnaround time can be improved if the most process finishes their next CPU burst time in a single time quantum. If the processes are completing the single time quantum, he's saying that average turnaround time can be improved. Option C, think. Option C is true. Option C. So average turnaround time of set-off process does not necessarily improve as the time quantum size increases. Yes. Average turnaround time can be improved. The most process finishes their next CPU burst time in a single time quantum. So you are telling false? Option C. Improved means what? What is the meaning of improved or improved? Average turnaround time can be improved if the most process finishes their next CPU burst time single time quantum. It is not taking more than one time quantum will get better turnaround time. Think on this. See, process have to wait more than n minus 1 q time to get their chance. Q is a time quantum, where Q is a time quantum. Process have to wait to get their chance not more than n minus 1 into q times. Yes, one process executed to get its chance, or any process want to execute to get the chance, you have to wait for all the process maximum worst case. So by damn sure I can tell option D is true. Option A also true, correct. Now think on B and C, very sensitive statement B and C. Yes, Nishukumar, what is option B? What is the response for option B? You understand here, when time quantum increases, when time quantum increases, it is not necessary. I mean, we cannot tell like, no, it can be increase or decrease. It not necessarily improves here now. It is not necessarily improves when time quantum increases. That is true. Average turnaround time can be improved if the most processes finishes their next CPU burst time in a single time quantum. What about C? Nishukumar, required response? Yes, if they are not taking more time, if they are not taking more turnaround, if more turnaround time is waiting time increases, isn't it? It is also effect on. It is also effect on. Yes, average turnaround time can be improved. The most process finishes their next CPU burst time in a single time quantum. Improved means what here? Increased or better, reduces. What is the meaning of improved here? That is placed very crucial point here. The average turnaround time can be improved if most processes finishes their next CPU burst time in a single time quantum. So reduces because you understand every process is finishing in a single time quantum, nothing but context switch overhead is less. Yes or no? Context switch overhead is less or not? Yes. Tell me. Suppose I am scheduled, this process is running only one time quantum completed. Now I get scheduling now. Context switch overhead is less, nothing but time quantum is reduces, right? Absolutely true. Absolutely true, this statement. So I hope this is clear now. So this kind of statement we should have a clarity. Everyone. Is it clear? Chalo, we'll move on to another question. So which of the following statement is are true? If the time quantum is extremely large, round robin scheduling behave like a non-preemptive SJF. If the time quantum is extremely large, round robin behave like a non-preemptive SJF. This is completely incorrect, isn't it? It will behave like a first come first serve. Am I right or not? When time quantum increases, it degrade to first come first serve. Right? If the time quantum is extremely small, the system throughput may decrease. Is it true? Option B true. If the time quantum extremely very small, the system throughput system throughput. Throughput means what? Number of process completed per unit of time. Decreases is saying that. True or false? Think. Okay. If the time quantum set to infinite, round robin reduced to first come first serve. This straightforward we can tell. If the time quantum equal to one CPU cycle, the system behave like a processor shared model. Yes. Where every CPU cycles context which happens, right? True. What about this one? Time quantum is extremely very small. The system throughput decreases. This also true. This also true, isn't it? Decreases. Number of process completion per unit of time reduces because every time quantum you are shifting. Time quantum when you are preempting context switch overhead increase. When context switch overhead increases, turnaround times of a process also increases, right? Yes, right. So BCD, B comma C and D are the right option for this statement, for this question. So I hope this is clear now. Moving on to this question, interesting question now. The arrival time, priority, duration of the CPU and IO burst of for each three process P1, P2, P3 are given in the table now. Each process CPU burst followed by IO burst followed by another CPU burst given. Assume that each process has its own IO activity is given. Operating system uses preemptive priority scheduling. What is the finish time of the process P1, P2, P3 dash? Can you work out? Can you work out this question? All of you work out. Completion time of three processes asking under preemptive priority scheduling algorithm. Under preemptive priority scheduling algorithm. Okay. So there are three processes are there, right? So let me take this value. Okay, let's draw the Gantt chart for this one now. Okay. CPU execution time start with a 0, isn't it? So are they given overhead, scheduling overhead here? No. Are P1, P2, P3 arrival time given, priority given. One is highest priority, bus times given now. That's it. Okay. We'll schedule P1. Okay. Now set time 0, minimum arrival time P1 is 0. I can schedule process P1 0. Its CPU bus time is what? 1 unit only, right? Its priority is 2, right? Its priority is 2. That's it. Right? Scheduling overhead is not given. Scheduling overhead is not given. Try it out. Try it out. Okay. P1 schedule, CP1 will run now. So at 1 immediately process P1 will go for IO activity. IO activity, how many units? 5 units are there now. So it will go 1 to 6, right? It will go 1 to 6. Who P1 will go now? When P1 shifted, my ready queue at next process P2 is coming at 2. So now 0, 1 to 2, 1 to 2. So CPU sitting ideal. At time T2, time 2, process P2 came. Process P2 can immediately process P2 can schedule now. Its priority is what? 3. I schedule this one now. But at 3, process P3 came. P1 was scheduled going on. P2 schedule right now. Schedule P2 is running. P2 is running 2, 2. So its bus time is 3 units required now. But at time 3, P3 came. Whose priority is 1? Whose priority is 1 now? Is it? Whose priority 1? Whenever a process running, if high priority process comes, you have to preempt it, isn't it now? So now P2 preempted, P3 schedule now. P3 schedule now. Leftover time for process P2 is what? 1 unit of 2 more units are there now. So P3 we schedule, P3 require 2 units time only, right? 3 plus 2, 5. So 3 plus 2, 5 now. Okay. Yet to 5, as soon as process P3 completes its CPU computation, it is going to be process P2 goes for IO. At 5, it required 3 instants. 5 plus 3, 8 till 8, it will run now. When P2 shifted here, okay, P3. So when P3 shifted, now P2 I can schedule it. P2 schedule now. Okay, P2 I scheduled it. So P2, how much time required? Leftover time is 2. But you know, whose P2 process priority is how much? 3. And P1 priority is 2. You understand now. So at 6, if you see at 6, so now P1 also completing. P1 come to what CPU state, isn't it? P1 completed IO activity, come back to, it is coming back to what? Ready queue now. Therefore, P2 will run only 1 unit of time. So P1 came. P1 has high priority over P2 because 1 is highest means what? 3 is lowest now. Therefore, P2 you have to preempt it, schedule P1 now. P1 schedule. So P1 IO activity over, now CPU computation will run now. 3 units now. 6 plus, right? 6 plus 3, right? 9. But you know, at 8, you understand when it is running this at 8. So P2 started at 5 IO activity. So P3, which process? P3 only, right? P3 started, not P. P3 started IO activity at 5. 5 plus 3, 8. At 8, P3 comes here now. P3 comes, right? Now P2 has run 1 unit of time. 1 more unit is there. 1 more unit is there now. P1 has run 2 units of time. 1 more unit is there, right? Okay. Now we have to schedule process P3 only. There is no option for me. P3 have to run 1 unit of time. So this, therefore P3 completed now. P3 completed. So which process have to schedule it right now? Who is there? P1 shifted. P1 is there now. P1 is there. P2 is there. P1 is highest priority. Schedule P1 now. P1 scheduled. So P1 process 1 unit is there now, 10. So now process P1 completed, right? Process P1 completed, if I am not wrong. Then so leftover process is what? Process P2 only, right? P2 you have to schedule it. P2 you have to schedule. P2 how much leftover? Only 1 unit of time leftover. At 11. At 11, you understand now. At 11 process P2 started its IO. So at 11 process P2 started IO, then plus 3. So this 14 it IO completes. At 14 process P2 comes. Now till 14 CPU setting ideal only. So immediately process P2 I can schedule it, right? P2 I can schedule. So only 1 unit of time. So the 15. Okay now. So process P2 completed 15, right? P3 completed at 9 only. P1 completed at 10. 10, 9, 15. Options are there. 10, P1, P2, P3, right? P1 completed at 10. P1 completed 10, correct only. P2 completed 15. So 15. So 15, yes, 9. Yes, option C is right. Option C is right. Correct? Huh? Those who are watching, just confirm me. 10, 9, 15. 10, 9, 15. No, no, no. P3, 15. P3 is 9. P2 is 15, ma. So can check P2 is 15, P3 9, P1 10. Correct? My values P1 completion is 10. P2 completion is 15. P3 completion is 9. 10, 15, 9. Yes. Yes, clear. Very good. Very good. Let's move to another question. There are many statements I given. We should know that which of the following statements are true. This type of questions help us handling what MSQ question now. Which of the following statements are true now? Shortest remaining time for scheduling may cause starvation. SRTF preemptions are there. Here it is favoring to shorter jobs. Longer jobs are get starvated. True. This is true. Preemptive scheduling may cause starvation. Yes. If you take preemptive priority causing starvation. Shortest remaining time first also. Preemptive algorithm is causing. But round robin is a preemptive algorithm. It is not causing starvation. That is the reason use the word may cause starvation, right? A is true, B is true, isn't it? Longest remaining time for scheduling does not cause starvation. LRTF, it is also favoring to shorter jobs, also limiting the waiting time of longer job. Therefore, it is not causing the starvation. SRTF is a starvation-free algorithm. Please understand. First come, first serve is better than round-robin scheduling algorithm in terms of response time. It is incorrect, isn't it? First come, first serve scheduling algorithm is not responsive, because if the first process is large process, remaining all process has to wait for them for it, right? It has a problem of what convoy effect problem it has. Round robin has a more responsive time than what? Responsive than the first come, first serve. Starvation problem is when low priority process might never get executed. That is true. Preemptive priority cases, you see, low priority process may not get executed, right? A true, B true, C false, D false, C false, C false. Longest remaining time first scheduling does not cause starvation. LRTF is not starvation, it is non-starvated only. F, aging is a solution to starvation problem where priority of a process increase with the time. True. Process with the same priority does not get executed by the CPU. This is false. Process with the same priority will run later, right? Processes with the same priority does not get executed. We schedule these processes by using process IDs, right? So I hope these statements are clear. Any doubt with the statements? Anybody having doubts with the statements? In LRTF, turnaround time will be more, but starvation won't be there. Please understand, Nishukumar. In LRTF, starvation will not be there. Long turnaround time increases. That's what the one statement I can clearly tell about LRTF. It is not only favoring to shorter jobs. It is favoring to shorter jobs, but also limiting the waiting time of our longer jobs. Yes, yes, yes. Chalo, we'll move for another question. Oh. So process state transition and events match list A with list B. Process situations and next are reasons here now. Shortage job first will suffer from starvation. Shortage job first will, yes, definitely suffers. Longer jobs are get starvated, isn't it? Yes, sir. Edge have a starvated algorithm only. It is interesting question now. You see it. List A, list B given now. Okay. 5 statement we have to map. Yes, this kind of questions can be expected theoretically, can be expected. A process has completed its IO request and now ready for CPU. A process has completed its IO activity over. If you are required, you can draw some transition. Now, here is a ready, right? Ready queue is there. Here is what running is a CPU state. So IO or block state, you understand, there is a new state is there, new state, right? So roughly drawing like this, So this is a connectivity, right? Preemption also there, right? Preemption will be there. Preemption. Here is a termination state is there now. So one process completed IO. Okay, is it now? Statement 1. A process has completed its IO request and it is now ready for CPU. So ready for CPU means it will go to ready queue only, right? So now we have to search this transition moving to this one now. So there is a transition ready to state due to IO transition to ready state due to IO complete. Transition blocks. Yes, this only, right? So can I say first one is mapping to 1, right? Transition to ready state only, na? Yes or no? Transition ready state only should go. Second one. A process was executing, but its time quantum expired. A process executing, time quantum expire. Where it will go? Ready queue it will go, correct or not? A transition ready now. Transition to block wait, no. Transition to ready state because the short-term scheduler need to reschedule it. A transition new to ready, transition from running to ready is a, so this only matching, right? Transition ready state you have to send it, right? So therefore second is mapped to 3. Third one, a process has been admitted into the system after long-term scheduling. Long-term schedule system submitting nothing, from where to where it will send it? New state to ready state only, right? So transition new to ready after admission of the long-term scheduler. Yes, correct. Therefore, we can say 3 is mapped to 4. A process issued a page fault while executing an instruction. When page fault occur, what happens now? Running process, you should go to block state, IO block state. You have to take the read a page from disk to memory now. Reading disk is IO operation, isn't it now? So transition to ready state, transition to blocked or wait due to an exception and condition is correct. So I can say it, fourth statement is what? 2. A process was preempted because high priority process arrived. Transition from running to ready due to preemption by high priority process. Straightforward, right? So the fifth statement is 5. Makes sense? Check it. Check it. Check these statements are correct. These statements are correct. Next question. Assume that OS contained 10 identical processes that were initiated at the same time. Each process contained 15 identical requests and each request consumed 30 milliseconds CPU time. The turnaround time of the first process, assuming round robin scheduling with a time quantum 20 millisecond and context switch time is 2 milliseconds dash. Turnaround time of first process under round robin algorithm. Try this question, very interesting question. Very interesting. Assuming that OS contains 10 identical process, I can write, process P1. So process P2, process P3, like this, process P10 are there now, that were initiated at the same time. Each process contain 15 identical requests now. 15 process are in 15 instances, you can tell. 15 requests, 15 instances. Each one having a 15. So 15 like this, each one have 15 is there now. Okay. And each request takes 30 milliseconds. 30 milliseconds, yes, of CPU time to run. Turnaround time of process P1 only they are asking now. Process P1, first process, assuming round robin, time quantum value given, time quantum is given 20 milliseconds. There is scheduling overhead also, 2 milliseconds is there. Scheduling overhead 2 milliseconds is there now. So time quantum under round robin policy. Okay. Under round robin policy now. Try this question. Try this question. All of you try it out. Try it out. So if you want to solve it, like you can minimize the problem, you can check it, then you can extend to this problem to for 10 year now, right? So one thing we can understand, suppose any number of process is there under round robin fashion, if you run it, if each process require more than one time quantum, time quantum is 20 millisecond, Each request require more than one time quantum, isn't it? Because 30 milliseconds, there are 20. So 20 means 10 more millisecond required, no? Each request of process require 2 time quantums, isn't it now? So for each, like you understand one thing now. When a process to get a chance, you have to wait for n minus 1 process, there one time quantum, then I'll get my chance, isn't it? Correct? Huh? So then you understand now all the process response also, I mean, they has to run, right? Suppose the second time quantum of P1 we will get, second time quantum of P1 we will get, second time quantum will get chance after running of all of them of their first time quantums, isn't it? Their first time quantums only, right? So work out, try to work out. Yes, any answer? So one thing we can understand, suppose we are looking for the process P1 to complete, right? Process P1 has 15 identical requests, right? So each request has 30 milliseconds, no doubt, right? Now she can say total time for this one, total bus times of entire process P1. So 15 into 30, isn't it? 450 milliseconds required. Any doubt? 450 milliseconds required. But 450 milliseconds will run continuously, right? Yes or no now? So number of times, number of schedules. The number of schedules for this process P1 equal to 450 by 20. Am I right? 20. Why? Time quantum is 20 now. What is this value? 22.5, isn't it? So 22 point nothing but compulsory required 23 schedules required, right? Any doubt? 23 schedules required, then only P1 will complete, right? What is the question here? Turnaround time. Turnaround time of the first process only asking now. Completion minus arrival, you can say now. All came same time only, right? All came same time only now. But if you same time also, we schedule by process ID manner only, right? 23 times process P1 we have to schedule it, then it get completed now. That means 22 times fully will happen at 23rd time is a 10 milliseconds will happen, isn't it? 23rd time, but that is also one time quantum, right? Right. Okay. Now understand, if each schedule, how much time this process will spend now. Here one more thing understand, now 23 times I have to schedule it, scheduling overhead for this process you take, scheduling overhead for this process will be 23 times into 2, 23. So 46 milliseconds required only scheduling overhead, isn't it now? So now total time of P1 if it has to complete nothing but this 450 plus this 46, isn't it? 496 milliseconds required. But if it is sequential, if I run it, only no other process present. If no other process present, if I context switch manner, if I do it, generally if no other process continue to run, but if taking context switch manner means overhead of context switch plus this many values have to take it now. But the point, other processes are there. P1 is other process, how many? 9 processes are there. All other are identical only, right? Every other process also require 450 milliseconds time or not. They also should run 22.5 contest means 23 times you should do it, isn't it? So 22 full, right? And 23rd is the last, right? That means, can I say now 9 process, 9 process, 22 times schedule, right? 22 times you schedule. 23rd is at last because P1 will get before only, right? I hope you are getting my point. I am repeating like this. P1, P2, suppose P3 is their assumption now. If P1 got chance, again P1 will get here. After these two process, P1 will get, right? So P2 required more than one time, nothing but P2, P3 also will be there here like this, right? So now P1 may complete. Suppose example, I'm taking scenario P1, P2, P3. All three require two time quantum assumption. 2 time quantums required assumption now. P1, if one time quantum over, second time quantum will come your chance. Second time quantum is this completes, this completion now. If P2 like one time quantum over, nothing but here is a second time chance. Here is a second time chance, right? P3 second time time now. I am not bothering this time. That's what 22 times I only have to consider. So remaining 9 process, 22 times I am scheduling, right? 22 times I am scheduling. Last when you schedule it, that will happen after P1 the last time quantum value only, right? We are not considering that part now. So 9 process, 22 times you schedule. Each schedule time, how much time this process spends? 20 is a time quantum value plus 2 millisecond overhead, isn't it? 22 only. Am I right or not? So this value, tell me now. 9 into 22 into 22. Somebody calculate and tell me this value. So 9 into 22 into 22. 4356, right? 4356. This all other process. But this process time also time considered. So turnaround time of this process will be 4356 plus this value. How much? 496, right? Plus 496. So 4852 is the answer now. The completion minus arrival. Arrival time anyway is 0. Therefore, this only value will come now. How's 22nd 22 comes, sir? So one thing you understand here, I am talking of first P1. Okay, now there are 10 process. Every process of 15 identical requests. Each request requires 30 millisecond, right? If I talk only one process total time, 15 into 30, 15 into 30, 15 into 30, 15 into 30 will be there. Make sense? So now process P1 time is what? 15 into 30 total time, 15 into 30, 450 millisecond required now. This 450 seconds will not continuously run it now. Run round robin. Each time quantum value 20. Number of times we have to schedule is what? 23 times you have to schedule it. Is it clear, Nishukumar? This line is clear. 22.23 times you have to schedule it. Is it clear? Okay. Now 23 times total. But 23rd time, no, 22 is a full, 23rd time is the only 10 milliseconds only, isn't it correct? Because 30 millisecond is the what time? My time quantum is 20 means what? Second time quantum always 10 only, right? So now 23rd is just 10 milliseconds will be the, who's this one now? Now come to the point now. Scheduling overhead I'm taking now. Every time, 23 times when you schedule it, Each time 2 milliseconds is scheduling overhead. So total 46 milliseconds now. P1 scheduling, this all completely 496 required. Is it clear? One process P1 now. It can happen for process P2 also, same thing. But only we are calculating the P1 time quantum well, time turnaround time, I have to calculate it. Now at one time, suppose you understand now. So suppose one process P1, when I scheduled it, every other process, remaining other process, first request you have to schedule it, is it now? Am I right or not? Now my point, remaining 9 process, that 9 process also 22 times you have to schedule it, isn't it? 22.5, but that last schedule I am not considering. So 22 times you have to schedule. Each schedule of other process, how much time will take? 20. Why is that 20 millisecond time quantum plus 2 what overhead is, right? Is it clear now? Okay, this is clear. After completing only, my process P1 will get a chance. I mean, I'm completing, right? So means my P1 will got this one, because every other last request will be there, that we are not considering. That's what I want example I given. P1, P2, P3. Once run P1, then P1 will get a chance after running of P2, P3, right? Right, n-1 process, they are n-1 process now. P2, P3 also will get after this one, right? We are not considering, we have to consider till this point only, right? That is the 9 process I have taken it. So 9 into this value. So now total time will be the 4356 plus this overhead, this total time. This other process time, my process time. So this moment, so completion minus arrival will be there. You can minimize or you can observe also. You can minimize and observe the problem also. So I hope the solution for this question is clear. Solution for this question is clear, everyone. Is it clear? So I would like to continue the session. Two more sessions I plan on operating system. So second and third session I'll be discussing IP synchronization and deadlock and memory and the file system. I'll be taking the 2 more sessions. So try to watch this all session, definitely useful to you and getting the more clarity over the concepts. Thank you all. Thank you so much for watching this video.